Okay, believe it or not, this is the last class before spring break. Before we all disappear to the beach, we have some chemistry to talk about. So what we're going to continue with today, as soon as you guys stop talking, is some topics related to chemical reactions that happen in aqueous solutions. So we've been introducing aqueous solutions as part of what Chapter 6 covers. And then as I sort of hinted at the beginning, there's going to be three types of chemical reactions in aqueous solution that we're going to talk about. We're going to talk about two of those today. Now before we get into that though, we're going to finish up a couple of topics related to molarity, and then I also want to go over today's work habit Wednesday, since it is Wednesday. So one thing that happens as the course goes on is as we start getting more test grades coming out, we have one so far, another one coming up soon, people realize the need to change their habits and start getting more help when necessary. And what I would say about my office hours is that they tend to be a fairly underutilized resource. So there's about 530, or I guess like 525 people in this class at this point, and I would estimate about 5 of them come to office hours regularly, meaning more than once and not like right before the test. So there's I don't have a lot of limitations on how, when you guys come, so I'm here most of the time. So even if the regular office hours don't work, so I encourage you to come more often if you feel like you're getting falling behind. And so what I want to talk about, in addition to just coming to office hours more, if you think that it would be helpful to you, which I think for most of you it would be, but in addition to office hours, there's tutoring. But from what I've heard from other students, I don't have the statistics exactly, but at the Chem Gym sessions, which is sort of the group review sessions that Launch offers, there's been about 20 students on average. Keep in mind that in addition to the 500 of you, there's about another 400 students taking Chemistry 1 in other sections. So what does that work out to? Roughly 2% of people are taking advantage of those resources. So I think we can certainly use those a lot more. And then going back to office hours, if you do decide to start coming on a regular basis, just some tips for how to make that time most effectively used, both for you and for me. So I think what the best thing to typically do is when you do your homework attempts, this is probably a good idea anyway, whether you ever plan to come see me in office hours or not. But I think it's a good idea to do all your homework attempts in a notebook and keep them organized, so which homework assignment, which attempt it is, so that way when you go back to look at problems, you have a clear record of what you've done. And in particular, if you come to office hours or tutoring to get help on those, what's helpful about that is I can look at the work that you've done on the problem to figure out which part of it you might be missing. Because a lot of times, especially in this part of the course, there's going to be problems that have many steps involved. You might have 90% of it down, you miss one little step and get the problem wrong, so you're not too far off. And if you come talk to me and you show me the work exactly that you did on that problem, I can usually identify, okay, here's the step you missed, and then you'll be able to fix that a lot more effectively. And so if you keep track of your work and keep it very organized, and you bring it with you when you come talk to me, that's, I think, a good way to efficiently use that time, and then make sure that we can very quickly identify which topics you need to brush up on. So a lot of times it's not a big thing, it's just one little thing you're missing, and if you're organized about that, it's easier for us to find it. I can always access your homework attempts, I can go back in to Blackboard and find them, but if you have no recollection of how you did that problem or how you got the number that you got, then it's harder for me to help you identify what exactly you need to fix. So these are some tips in here that you can look at, and again, just a regular encouragement to come to office hours if you feel like there's anything you want to discuss in this course. All right, so with that, we'll get into the chemistry, and what we ended up with last time was the topic molarity, which is a concentration unit that we can use to define how much solute is dissolved in a volume of solution. So what we learned about last time was how to calculate molarity, and what we're going to start with today is just a quick example problem on how to use molarity as a conversion factor. We're going to come back to this a lot more at the end of the chapter when we start discussing aspects of stoichiometry that pertain to aqueous solutions. So we're just going to go through one example today, but then this type of conversion is going to be something we'll do a lot more towards the end of this chapter. Okay, so in the problem we have here, hemoglobin is a protein found in red blood cells, and then heme would be a part of that. So how many heme molecules are there in 25 milliliters of a solution that has 0.00150 molar? And so what we kind of alluded to last time but didn't do any examples with is that molarity now gives us another conversion factor involving moles. So in chapter 5, we learned the relationship between moles and number of atoms or molecules, and also the relationship between mass and moles, which being the molar mass. Now we have another one, which is molarity, because remember that capital M here means moles per liter, specifically moles of solute per liters of solution, and so it can relate those two quantities as a unit conversion. So what we're looking for in this problem is the number of heme molecules. And since we're looking for a number of molecules, we will use Avogadro's number. We should recognize that. But before we can use Avogadro's number, we have to convert to moles first. So we're not given moles, we're given volume of solution and molarity. So let's learn how to use those two to give us the number of moles. So the first thing to keep in mind is that the volume that we're given is 25.0 milliliters. So we're going to typically start with that. We're going to use molarity as a conversion factor. But before we can use molarity, we have to recognize that the volume is in milliliters and molarity is moles per liter. So as I said, very often you're going to have to convert milliliters to liters before you use molarity. And so what we're going to do is we want milliliters of solution. Let me write it out as solution so we can have that more clearly labeled. We want to convert that to liters first, okay? So 1 liter of solution will have a volume of 1,000 milliliters, so we can convert from milliliters to liters by dividing by 1,000. And then when we're doing problems like this that involve molarity and trying to find number of moles, once we have liters of solution, we can use the molarity as a conversion factor, all right? So what we want is we want liters of solution to cancel out, and we want to get into moles of the solute, which in this case is heme. And what we remember is that molarity tells you how many moles there are in 1 liter. So we're going to use that number as a conversion factor, 0.00150 moles of heme in 1 liter of solution. Okay, so this ratio allows us to convert volume of solution into moles. And then once we have moles, we can use Avogadro's number to figure out how many molecules that corresponds to. So 6.022 times 10 to the 23rd heme molecules in 1 mole of heme. So those units cancel out and we get to what we're looking for, which is the number of heme molecules. And the number that I got was 2.26 times 10 to the, is that a 19, I think? Yep. I can't read my own writing, so I know how you guys feel. All right, 2.26 times 10 to the 19th heme molecules in this solution, all right? So again, not in practical terms, we usually need to know the number of molecules in a solution, but we can use molarity as a conversion factor now that involves moles and is another relationship. So as I said, we're going to formalize that a little bit more when we talk about stoichiometry, and we're going to use that relationship, molarity as a conversion factor, a lot as we deal with that. But for now, we're going to move on. And the last thing we're going to talk about with molarity, which is sort of an isolated topic. This is not something that's going to persist for a long time, but we're going to talk about dilution. So there's a saying in the chemical industry that dilution is the solution to pollution, but I don't agree with that. But we're going to learn just what dilution is and how to do some calculations involving it. So the first thing to keep in mind is let's talk about, in a sort of a pictorial sense, what dilution is. So what we're going to do so the definition of dilution is we're going to take a solution that has some concentration. So what I'm drawing here, blue is the solvent. In reality, we wouldn't be able to see the solute particles because it's a solution, so it's homogeneous. But let's say we could identify in red the solute, and make sure I count those 1, 2, 3. So I have 8 solute molecules. All right. So just again in a pictorial sense. So we're starting with a solution with some molarity and some volume. And what you're doing in dilution is you're going to add pure solvent to a solution, or vice versa, add the solution to pure solvent. And then what you're going to do is that's going to make a new solution that has a lower concentration. So in dilution, all you're doing is you're changing the concentration of the solution, and the volume as well, by just mixing the solution with pure solvent. So you're not changing the chemical identity of what's in solution, you're not doing any sort of chemical reaction, you're just changing its concentration. So what we do is we start with a solution that has, relatively speaking, a larger molarity in a smaller volume. And then we're going to mix that with pure solvent. So we have another beaker with pure solvent in it, and then we're going to take this solution, we're going to mix them in. And then what happens is that all of the solute molecules that are in the original solution are going to end up in the larger volume solution down here. So you're not going to lose any solute molecules because they're all going to be transferred into the new solution. So this is still going to have the same number of solute molecules, 8 as I've drawn it in this very generic cartoon form. But the point is that these solute molecules are now dissolved in a larger volume. And so the new solution that you produce is going to have a larger volume because we've added it to pure solvent, so we've increased the volume, but it's going to have a smaller molarity. Okay? And so the whole point of this is when we do dilution, we're not going to change the number of moles of solute that we have. So the moles of solute is going to stay constant during the dilution process. So it's going to be the same before and after dilution. All we're changing is the volume that those solute molecules are dissolved in. All right, so we're keeping the number of solute molecules the same. We're just, let's make this a little bit smaller. Wrong way. All right, so so that's how dilution works. We're not changing the number of solute molecules, we're just changing their concentration. So then let's learn the one equation you need to know for dilution. So these types of problems are pretty straightforward because there's not a whole lot of layers to this onion. Basically what we have is, if we remember the definition of molarity, which is moles of solute divided by liters, or volume of solution, in liters specifically, but for this we're going to just use the more generic label V for volume of solution. And then if we take the product of those two, so we're going to basically cross multiply here, we're going to move the volume over to the left side. Molarity times volume is equal to moles of solute, in particular if the volume is in liters, but we're going to have this relationship. And remember that in a dilution situation, the initial number of moles we have before dilution is equal to the number of moles we have at the end, so we're not changing the number of moles. And so then what that means is that this product, molarity times volume, is going to be the same before and after the dilution. And the way that we write that in equation form is that M1V1, the initial molarity times the initial volume of the solution, is equal to M2V2, the final molarity times the final volume after dilution. This equation only applies generally to dilution. When we start talking about stoichiometry towards the end, people are going to be tempted to use this for that, and it's not good to do that because it will sometimes work, but most cases not. So we're really only going to use this when we're doing dilution, which is not a chemical transformation, it's just taking a solution and changing its concentration. So M1V1 equals M2V2, that's the dilution equation, that's the only one you need to know. And as we'll show as you do a couple of example problems, the molarity is always going to be molarity, moles per liter, but we don't necessarily need to use liters as our volume, because as long as the two volume units are the same, the equation will work, okay? So we'll see that as we go through the example problems. All right, so a typical problem for this would be, what volume of 6 molar NaOH is needed to prepare 250 milliliters of a 0.5 molar solution? All right, so again, the dead giveaway that this is a dilution problem is that we just have one solute, NaOH, we're not reacting that with anything, we're not doing any sort of chemical reaction, and we have two different concentrations. We're starting out with a 6 molar solution, and we're ending up with a solution at a lower concentration. So if you see those two things, just one solute that's not changing its identity or reacting with anything, and it's just molarity that's changing in volume, then we should identify this easily as a dilution. And so then let's go through. We have the dilution equation, M1V1 equals M2V2, and basically we have to figure out which of these are we solving for and then solve for it. In reality, it's arbitrary. What you use is M1 in V1 and M2 is in V2. Conventionally, I will call M1 and V1 the initial and volume and molarity, and M2V2 the final, but if you switch those, it's okay because the equation still works. So what we're looking for is, this is our initial molarity, the higher concentrations we're going to start with, that's our M1, and we're looking for what volume of that solution, so that's V1, that was to be unknown, so what volume of that solution is needed to prepare 250 milliliters, this is V2, of 0.5 molar solution, so this is M2. All right, so again, in problems like this, you're going to typically just, you pretty much to do this type of problem, you can only have one unknown. The rest of these are given to us. So we're solving for V1, the volume of the first solution that we need to do this dilution, which is going to be M2V2 over M1. And so we just have to plug in the information to get this. So the initial volume, V1, what volume of this higher concentration solution we're going to use is M2V2. So the final molarity is 0.5, capital M molar. The final volume is 250 milliliters. In this problem, as I said, it does not matter what volume unit we use as long as we're consistent. So we're going to take that product and we're going to divide it by the initial molarity, M1, which is 6.00. So the units molarity cancel out, and then the number that we'll get when we multiply and divide is going to be a volume in milliliters. So pay attention to units, because whatever units you use, you need to make sure that if you're using both volumes in the calculation, they need to be the same. In this case, we're solving for a volume, which is going to be what our final answer would be in milliliters if we use that number directly. And what we get is 20.8 milliliters. So I didn't specify a unit here, but most often you're going to be reporting volumes in milliliters. Okay? And so what this means is that if we take 20.8 milliliters of 6 molar NaOH solution, and then we dilute it with enough water to change the volume to 250 milliliters, the new concentration is 0.5 molar. Okay? Yes?
Don't we record molarity in moles per liter?
Yes, but in here we have molarity in the numerator and the denominator, so they cancel out. So whatever volume unit we attach into this calculation for V2 is going to be the volume that comes out in our final answer.
Normally we're going to just go with the unit we're given, right?
Yeah, the problem will specify, usually if it's a numerical problem, what volume in milliliters or what volume in liters. Most often milliliters, but not always. But like I said, so and then alternatively, let's say we were solving for M1 instead, M2V2 over V1. If this was the calculation we were doing, as long as the two volume units are the same, it'll work, because those units will cancel out in the numerator and denominator. So they could be liters or milliliters, whatever is convenient for that problem. So for this type of problem, you don't need to use liters. It's not wrong to use liters, but you don't have to. Yep. Anything else? All right. One last dilution problem, which this probably takes it a step further than we need, but it does help us think about a lot of concepts and connect a lot of things together. So if we have concentrated phosphoric acid, that's going to be, so when we talk about a concentrated acid, that's basically the maximum amount of acid that you can dissolve in water, or that would be combined with water. So if concentrated phosphoric acid, which is going to be mostly phosphoric acid, is 90% by mass, so that means 90% of the mass of that solution is phosphoric acid, the other 10% is water. That's the concentration in percent mass, and it has a density of 1.5 grams per milliliter. How many milliliters of this solution are needed to prepare 2 liters of a 0.1 molar solution? And then we gave you the molar mass here as well. So this should be recognized as a dilution problem, because we're just, again, figuring out changes in concentration and volume. So M1V1 equals M2V2. And what we're looking for here is, again, what volume of the solution, the initial, so it's similar as the last one. We have, in this case, a concentration in mass percent. We're looking for how many milliliters of that solution, so we're going to solve for V1. And then what we're given at the end is the final molarity is 0.1, and the final volume is 2 liters. So we have M2 and V2. So what we're going to look for is V1 again, just like the last problem. The difference here is that M1 is not directly given to us, okay? Because in order to use this equation, both concentrations, M2 and M1, need to be in molarity for this to work, and our M1 is not given to us in moles per liter. It's given to us as a mass percent. So what this problem first asks us to do is figure out how to convert mass percent into molarity, something we haven't covered yet, but the concepts, I think, should all be there. We just have to figure out how to piece them together. So if we want to find what M1 is, we have to do a little bit of work in this case to get that. So we're starting with 90% by mass, and remember that the definition of molarity is moles per liter. So that's what we're looking for, is a concentration in moles per liter, and the concentration that we're given is a mass percent, which means that we have 90 grams of H3PO4 per 100 grams of solution. So that's another way of writing mass percent. Remember that percent is per 100 grams if we're talking about mass percent. So this is what we're initially given, a ratio that's 90 grams of phosphoric acid per 100 grams of solution. What we have to do is convert the numerator to moles and the denominator to liters of solution. And if we do that, that will convert this number into molarity. All right, so how do we convert grams into moles? Well, that should be old hat for us by now. So if we want to convert the numerator, which is 90 grams of H3PO4, into moles, we just need to use the molar mass that we're given. So 1 mole of H3PO4 has a mass of 97.99 grams. So by dividing by that number, we've converted the numerator, which is in grams, into moles. So that part is taken care of. So we're in moles. Now I just need to get the bottom, which is grams of solution, into liters. And for that, we're going to end up using the density. So the density is given as 1.5 grams per milliliter. So if we use the density of the solution, we can convert grams into milliliters. So how do we do that? We want grams to cancel out. And then we want milliliters in the denominator. We eventually want to get to liters, as we said, but we don't have a direct conversion, so we're going to go to milliliters first. And we're going to just use the density as given to us, 1.50 grams per 1 milliliter. And so that allows grams to cancel out, and now we have milliliters in the denominator. And then the last step is to convert milliliters to liters to make sure that we have it now in terms of moles per liter. All right, so we want milliliters to cancel, and those are in the denominator, so we want So this is the way we're going to do it, and the conversion factor is 1,000 milliliters in 1 liter. So that cancels out the milliliters, numerator here, denominator here. We now have liters in the denominator, we have moles in the numerator, and so multiplying this across gives us 13.8 moles per liter, which is 13.8 capital M molar. Okay? So in this case, we do not directly have M1, but now we know what the number is, 13.8 molar. So once we have the initial molarity in the correct units now of moles per liter, we can just use the dilution equation that we already introduced in this problem. All right, so the way that works is we're going to, again, find V1, the volume of the more concentrated solution we need for this dilution. And now we have all the quantities we need, okay? So it's going to be M2 and V2 is 0.1 molar is the final molarity. And the final volume is 2 liters. Again, we can use any unit we want for volume in these types of problems. And then the M1 that we just solved for is 13.8. All right. Again, we have to pay close attention to units because when we do this, the number that we get is 0.0145, but the units is liters. And this problem asks for how many milliliters, so we have to do one last conversion, 1,000 milliliters in 1 liter to get it into the correct units. All right. So always pay attention in Blackboard which unit we asked for. So 14.5 would be the answer in milliliters. Alternatively, we could have put milliliters directly into this equation. Instead of putting 2 liters, we could have put 2,000 milliliters, and that would have given us this number directly. So a couple ways of doing that, but we just have to make sure that we end up with milliliters because that's what the problem asked for. All right, so that one just required the additional step that we covered previously of converting mass percent into molarity. Now, this course does not make a big deal out of different concentration units besides molarity, so chances of you seeing something like this on a homework assignment or a test are pretty slim. In Chem 2, you'll cover some other different concentration units besides molarity. So for now, we're going to primarily stick with molarity, but this problem, I think we have all these concepts that we just had to figure out how to put together. So using grams to moles and then using density as a conversion factor, all that stuff we've seen before, this just uses it in a slightly different way. All right, so any last questions on dilution before I move on? Okay, so now we're going to start talking about are the different kinds of chemical reactions that happen in aqueous solution. So there's going to be 3 types that we'll cover, 2 of them today, 1 next time. The first one that we're going to talk about is a precipitation reaction. So if you have a really good long-term memory, I mean, this is my 6th time teaching the course, so of course I remember it, but if you guys remember back to, I think it was the very first day of class, we talked about law of conservation of mass, and I showed you a video of a chemical reaction where they weighed the contents before and after the reaction. They didn't change. That demonstrates conservation of mass. If you remember that reaction, they started with 2 clear colorless solutions, and they mixed them together, and they got like this sort of cloudy yellow mixture. That was a precipitation reaction. It's actually the one we're going to use today as an example. So what's the definition of a precipitation reaction? It's when we take 2 solutions, so again, 2 homogeneous mixtures where everything is dissolved, and we combine them. And then what happens is, after combining them, 1 or sometimes more than 1 insoluble products forms, okay? So something that's insoluble is something that doesn't dissolve in that particular solvent. So what it does is it forms a solid that precipitates, as we call it, from the reaction mixture. And you get usually a cloudy mixture or a solid that sort of falls to the bottom. And that's what a precipitation reaction is. So you're starting with 2 solutions, but you're ending up forming a solid insoluble product that is no longer dissolved at the end of the reaction, okay? So the first thing we need to figure out is when you're looking at precipitation reactions, one of the things we will often ask you to do is, okay, if we mix together solutions of these 2 compounds, will you or will you not get a precipitation? So in other words, will it happen, and what will be the identity of the precipitate? So the steps to doing this are, this is going to involve mixing together 2 solutions of ionic compounds. So remember that when ionic compounds dissolve in water, they separate into their individual ions. So the first thing we're going to do is we're going to figure out what are the ions that are present in the 2 reactants. Okay, so we're going to separate the reactants into their constituent ions, the ions that make them up. These are, again, ionic compounds. So when they dissolve, the ions separate. So initially the reactants are going to be dissolved, and they're going to separate into ions in that solution. So this is the 2 things that they mixed together in that video, although I didn't really talk about it at the time, was potassium iodide as an aqueous solution, and they mixed that with an aqueous solution of lead nitrate, lead 2 nitrate specifically. Okay, so if we mix these 2 things together, we have to think about what are the ions that are going to be present in solution. And if we're just trying to identify which products form and whether they're soluble or insoluble, we don't necessarily need to worry at this point about the stoichiometry or the number of ions. We just need to think about what they are. So when potassium iodide dissolves, we're going to get K plus as an aqueous solution, and also I minus. So those are the 2 ions that make up Ki. And then the other one, which is lead nitrate, we're going to have lead 2 plus as the cation. And then again, if we do want to include coefficients, because there's 2 nitrates in the formula, when we dissolve this, we're going to get 2 nitrates dissolved as an aqueous solution. Again, for now, for just the point of identifying the precipitate, we don't have to worry too much about coefficients and, stoichiometry and all that stuff. But these are the ions that we get. The 2 ionic compounds, when dissolved, will separate into these ions. And then what we have to think about is, what are the new combinations that can form when the 2 are mixed together? So typically you're going to have 2 products that are possible. And the way that you get those 2 products is you just swap the cation and the anion. So the cation from the first reaction, which is K plus, is going to be paired up with the anion from the second reactant, which is NO3 minus, to get the other combination. And then similarly, the cation from the second reaction, which is lead 2 plus, is going to pair up with the anion from the first reactant, I minus, to get that other combination. So you're just going to swap cations and anions. So what we get here is K plus with NO3 minus, which makes potassium nitrate, KNO3, as one product. And then lead 2 plus with I minus, the correct formula for that would be PbI2, because it's a 2 plus cation with 2 minus 1 anions. So these are the 2 products that we get. And then to identify, is this a precipitation reaction, and if so, which one of these precipitates, which of these 2 products? To determine that, we have to use what are called solubility rules. And anybody that's taken chemistry before is probably already groaning, because this is understandably not everyone's favorite topic in this course. So what it seems like is, especially if you read the book, it seems like a sort of a random collection of unrelated rules that you have to memorize. What I'm going to try to go through today is a little bit more of a systematic way of thinking about it, or at least a way to sort of help you identify some of the obvious cases to then narrow things down for you. So let's go through solubility rules. Basically, solubility rules are a set of rules that allow us to predict whether an ionic compound is or is not soluble based on the combination of ions that it has, okay? So the first thing you want to look for are the ions that are always soluble, because in this category, if the ionic compound has one or both of those ions, even just one of them, it will be soluble, okay? So there's going to be a set of cations and a set of anions that fall into this category, okay? So if an ionic compound has one of these cations, it will be soluble no matter what the anion is, okay? So the cations are going to principally be the group 1A cations. That's going to be the alkali metals. So lithium, sodium, potassium, rubidium, and cesium. So if that's the cation in your ionic compound, then you can assume that it will be soluble. And then the other one that behaves this way, which is not as obvious, is a polyatomic cation, ammonium, NH4+. All right, so these cations, if that's the cation in your ionic compound, it will be soluble, no matter what the anion is. And then similarly, we have some anions that behave the same way. If one of these anions is in your compound, then it will be soluble, no matter what the cation is. And so those anions, the ones that we'll see, at least in this course, are nitrate, NO3-, perchlorate, ClO4-, and then acetate, which is a weird polyatomic ion, CH3COO-, or sometimes written as just C2H3O2 with a minus charge. That's acetate, okay? One of our polyatomic ions that we should know by now. The one that I'll underline as being by far the most common that we'll see in this course is nitrate, NO3-. So if you see nitrate in your compound, or one of these other two, not as common, then you can bet that the ionic compound is soluble, no matter what the cation is. So these are the ones you want to look for first, because if you see one of those in one of your products, that will be soluble. It will not be your precipitate. It won't be involved. And then we also have a category of primarily some cations and anions that are always insoluble unless they're paired with one of these. So again, there's sort of a hierarchy to these rules as well. So all these will always be soluble no matter what they're paired with. We then have a category that will always be insoluble unless they're paired with one of these. So if we have the cations that fall into this category are going to be silver plus and lead 2+. So any ionic compound that has silver plus or lead 2+ will be insoluble unless the anion is NO3-, perchlorate, or acetate. So unless it's one of these anions, these will give insoluble ionic compounds with any other anion. And then if we have a group of anions that are going to fall in this category as well, you would have carbonate, CO3 2-, phosphate, which is PO4 3-, sulfide, S2-, chromate, COO4 2-. These will always be insoluble unless they're with one of these cations up here, okay? So these are probably the ones you want to look for first, because these are fairly obvious ones, and if they show up in your problem, you can quickly identify that that compound is or is not soluble based on whether it has one or both of these ions in it. All right, and then we have another category which would be the usually soluble ones, unless these are anions, unless they're paired with one of these cations, okay? So if we have the halides, so if this is our anion, Cl-, fluoride doesn't really fall into this category, but these three common halides, chloride, bromide, iodide, do. And if this is your anion, the compound will be soluble unless these are your cations. And there are actually two other exceptions too that I have to put down here. So this one is not as straightforward, but again, if you see a halide in your formula, in most cases it will be soluble, except for silver plus, lead 2+, and then also copper plus, and then mercury 1, which exists as a diatomic cation, so Hg2 with a 2+ charge overall. Not as common as silver and lead, but those are also insoluble halides, okay? So the halides are usually soluble except for those 4 cations. The 2 that I listed up here and the 2 that I've listed down here as other exceptions. So look for halides as well. They're usually soluble. The last category that I have to talk about are what I call the in-between annoying ones. These are ones that probably have as many exceptions as they have rules, so they're kind of irritating in that respect. So there's two anions that I would put in this category, which are sulfate, SO4 2-. This one is also usually soluble, but it has more exceptions. So it's soluble unless it's paired with one of those category B cations. So as we said, silver 1 and lead, those are going to be insoluble unless it's nitrate primarily. So if it's sulfate, that will still be insoluble. But then other exceptions are going to be the heavier group 2 cations, calcium, strontium, and barium, the ones at the bottom of the periodic table in group 2. These will make insoluble sulfates, okay? So there's more exceptions for sulfate, which is why it's a little bit harder to remember sometimes. And then similarly, OH- hydroxide, this one more often than not is insoluble, but it also has a lot of exceptions. So it's going to be insoluble except with those category A cations that are always soluble. So sodium, lithium, and so on. And then it has actually the same exceptions as sulfate, but in the opposite sort of sense. So the same exceptions, calcium 2+, strontium 2+, and barium 2+, but in this case, these three hydroxides would be soluble, not insoluble. So same exceptions, but this time it makes it soluble as opposed to for sulfate, which makes it insoluble. So those ones are probably the two hardest to keep straight of the ones that you will commonly see. And the reality is that for solubility rules, there's no easy way to look at the formula of a compound from first principles and just predict whether it's soluble or insoluble. You really just have to internalize these rules. But like I said, if you learn the first two up here, that's going to take care of the majority of cases. And then these ones are going to show up from time to time, be a little bit more difficult. But I would encourage you to follow sort of this approach. This is what the book gives you, which is just a list of 6 rules that aren't really sort of characterized in any sort of hierarchy. I think the way that I presented it is at least a slightly easier way of learning it. And we can, go from there with how to sort of characterize compounds as soluble or insoluble. Okay, so that you're just gonna have to learn. Yes. Halides are the group 7 elements. So that's that second to last column of the periodic table: fluorine, chlorine, bromine, iodine, and those form -1 anions, which are called halides. And so especially Cl-, Br-, and I-, those are usually soluble when they're part of an ionic compound. Okay, so it's just these 3 that you have to worry about.
So is there a difference between halogens and halides?
Halogen would be the neutral element, like Cl-Br-I. Halide would be the one with a negative charge when it's an anion. Okay. All right. So that's going to be solubility rules. You're gonna hate me for having to learn this, but I'm used to it, so just deal with it. All right. So then. All right, so let's talk about now chemical equations for aqueous reactions, in particular those that involve precipitation that we've been talking about. So there are actually 3 ways of writing a chemical equation for an aqueous reaction. We're going to cover all 3 of those. The first and the last being the 2 most common that you'll use. So the way that we're going to usually see this, especially if we were just doing a stoichiometry problem and just had to write out a balanced equation for that, would be what's called the molecular or formula equation. And so in this setup, what you're going to do is you're going to put the full set of reactants and products without separating them into ions and writing them just as intact species. Okay, so it's going to be the full set of reactants and products written as intact species. So for the formula equation, we don't separate ions, even though that's in reality what's happening in solution. We just write them together. Okay. So the way you would do this for the reaction we talked about earlier, potassium iodide and lead nitrate, would be you have Ki, and remember the reactants in these are going to always be aqueous. They're going to be dissolved in solution. So you have aqueous Ki and then aqueous lead nitrate are the 2 reactants. You're just going to write them like this without separating anything. And then on the product side, remember we're going to swap cations and anions, so we're going to form KNO3 and then PBI2. And then on the product side is where we have to decide whether either of these are insoluble or not. So before we do that, let's put coefficients in. So what you'll see is that these are typically not too difficult to balance. Usually ionic reactions have coefficients of like 1, 2, or 3 at the highest. Sometimes in rare cases, maybe a little bit larger than that, but generally speaking, you're going to have pretty small coefficients for these. So what we'll see is we have 2 iodines on the product side, so we need a 2 there. And then we have 2 potassiums on the reactant side now, so we need a 2 there. So usually coefficients of not very large numbers are going to be needed to balance these. And then so now the reaction is balanced. What we have to think about, as I said, is the solubility of the 2 products and deciding whether we should write those as aqueous, still dissolved, or as a solid forming a precipitate. So potassium nitrate contains both K+, which is a group 1 cation, and NO3-, which is the anion that's always soluble. So both of those being always soluble species will mean that this species is soluble. So we're going to still keep that as AQ because that will stay dissolved because that follows the solubility rules for a soluble compound. And then for lead iodide, remember that lead compounds are almost always insoluble unless nitrate's the anion. So when we make lead iodide, that will be an insoluble compound by the solubility rules we just covered. And so we're going to put a little S next to that to indicate that that's no longer dissolved, but forms a solid precipitate. Question?
Isn't there supposed to be a 2 next to NO3 in the product, the reactant?
There's a subscript of 2 that I left out, yeah. So there's going to be a 2 here once it lets me write it. Come on. Oh, no.
I'm sorry.
Sorry, I won't blame you. I don't know, this program's gotten more flaky as time has gone on. It usually recovers most of it, so it's not too upsetting. It's a bigger problem when the video crashes, which has not happened this semester, knock on wood. All right, so this is going to come back. We'll see how much of the notes get recovered so I don't have to rewrite them. Usually the last one that I was working on when it crashed does not come back, but we'll see. We're good, we're good. Yeah, we lost that page as expected. Okay, no big deal. Okay, so then what we said before is molecular equation is the full set of reactants and products written as intact species. So for molecular equations, we're not going to separate anything. And what we basically finished writing out before that technical glitch was we had this chemical equation here, which is balanced and then uses these little labels next to the reactants and products to tell us whether it's dissolved, aqueous, or not dissolved as a precipitate, meaning it's a solid with the S. So what we got was this, and there's a 2 there that I almost forgot again. So there it is. And then we get 2KNO3, which we said is soluble based on our solubility rules, so that's going to stay aqueous. And then we get lead iodide, lead 2 iodide, which is insoluble, so it gets a little S next to us, indicating that that's the precipitate. So this would be a precipitation reaction, and this would be the identity of the precipitate. So that yellow solid that formed, if you remember the video from back on the first day of class, that was lead iodide forming as a precipitate in that reaction. All right, the other way that we can write this one's not as common, but in some cases it's helpful to write this out to be able to get from the molecular equation to the last one, which is net ionic. So sort of the intermediate point is the total ionic equation, where we're going to separate anything that's soluble, anything that has an AQ next to it, we're going to separate it into its individual cations and anions, which is what happens when those things are dissolved in solution, as we know. Okay, so we're going to separate soluble ionic compounds, which are the ones that have AQ next to them, into their individual ions. Okay, so this is sometimes takes a long time to write out, but if we look at in the reactant side, everything's going to be soluble, so we're going to separate both of these into ions. So 2Ki is going to separate into 2K plus and 2I minuses because there's a coefficient of 2 in front of that. Lead nitrate is going to separate into Pb2 plus, lead 2 plus, and then it has the 2 that I kept forgetting and now is there, so 2 NO3 minuses. And then on the product side, the first product, KNO3, is still soluble, so it's we're gonna separate into ions as well. So 2K plus and 2NO3 minus, because the coefficient of 2 modifies both of those ions in the formula. But then the last product, which is PBI2, because it's insoluble, we don't want to separate that. That's going to still be a solid, and so we just write that the same, PBI2 solid, okay? So anything that's aqueous, anything that's soluble, we separate into ions for the total ionic equation. Now this is kind of long and unwieldy, but then what that leads us to is what's called the net ionic equation, where we're going to remove what are called spectator ions, okay? So the spectator ions are the ions that appear on both sides of the arrow, and we're going to get rid of those to write what's called a net ionic equation, which only deals with the ions that are sort of changing their form during the course of the reaction. All right, so spectator ions appear on both sides of the equation, and we haven't really talked about this yet, but if you have a chemical equation and it has something that appears on the left and the right, in net nothing is happening to that, so you can kind of cancel it out, almost like a mathematical equation. If you have x on both sides of the equal sign, it cancels out because you subtract it from both sides. So if we look at this equation here that we just wrote, we see that we have 2K plus on both sides of the arrow, so that's one of our spectator ions would be K plus, and we also have 2 NO3 minuses on both sides of the arrow as well, both aqueous, so in the same form on both sides of the equation. So these are our spectator ions, K plus NO3 minus. So in the net ionic equation, we get rid of those and we only keep the ions that are involved in the net chemical conversion. So typically we write cations first and then anions, although it doesn't have to be that way. So what's left in the net ionic equation is lead 2 plus on the left side, 2 I minuses on the left side, and then on the product side, we just have PBI2. So in a net ionic equation for precipitation, what you usually have is on the left side, you have the 2 ions that are going to then combine to form the precipitate. Anything that's soluble on both sides drops out as a spectator ion. All right, so these are the 3 ways of writing the same chemical equation. Again, the most useful one's probably the first and the last. But we will ask potentially about all 3 of these in how to write the equations in different ways. Okay, so that's So let's do some examples just to see how this works in some other contexts. So we're going to write all 3 of these molecular, total ionic, and net ionic equations for the reaction that occurs between sodium sulfate and silver 1 nitrate. All right, so as is often the case, we have to know to be able to convert the names into formulas to be able to write out the reactions and products. So these are the 2 reactions that we have. So we start with the molecular equation. This is typically how we're going to do it no matter what we're asked for. So one of the reactants is sodium sulfate. So recall that sodium is in, let me pull this up. Sodium is a group 1 cation. So it's going to form a +1 cation. And then sulfate, we have to remember, is SO4 2 minus with a 2 minus charge. So the correct formula for sodium sulfate is Na2SO4. That was stuff that we learned back in chapter 3, I believe it was. So that's one reactant. The second reactant is silver 1 nitrate. So it's going to be AgNO3. Silver 1 means it's a +1 cation. Nitrate is -1 anion, so we just need one of each in the formula. And then the 2 products are going to be where we swap the cations and the anions. So we're going to take Na plus and combine it with NO3 minus to make sodium nitrate, which is just NaNO3. And then we're going to make silver sulfate, which is Ag+1 with SO4 2 minus. So the correct formula for that would be Ag2SO4. +1 cation, 2 minus anion. And then we're going to need some coefficients to balance this. So we're going to need a 2 there and a 2 there, and that should get us balance on both sides. Typically for balancing these, you don't necessarily need to think about the individual atoms that are involved. You can just think about the ions. So we have 1 sulfate on the left, 1 sulfate on the right. 2 sodiums on the left, 2 sodiums on the right. 2 silvers on the left, 2 on the right, 2 nitrates, and so on. So we don't have to break it down as far as we did before with other types of equations, because in this case the ions themselves are going to all stay together, just combine in different ways. And then we have to think about, to write this out, which of these is soluble and insoluble. So dead giveaway, this has sodium plus and nitrate in it. Both of those are always soluble, so that's going to be AQ, just like we saw KNO3 before. And then silver is a cation that is almost always insoluble unless it's with nitrate, pretty much. So that's going to be our precipitate with an S next to it. All right, so that's our molecular equation. And then for the next step, we want to write the total ionic. And so remember, for a total ionic, what we're going to do is we're going to take anything that has an AQ next to it and divide it up into its individual cations and anions. So on the reactant side, we have sodium sulfate, which is going to dissolve. So we're going to get 2 sodiums from that. And a sulfate, SO4 2-. So we still need to think about names and formulas of polyatomic ions for this part. And then in this reactant here, we get silver plus and NO3-, coefficient of 2, so we're going to get 2 of each of those. So in a total ionic equation, you're going to typically separate, for precipitation reactions in particular, you're going to separate both things that are on the left side, because those are both soluble ionic compounds. And then on the right side, we're only going to separate the one that has the AQ next to it, which is sodium nitrate, so we're going to get 2 Na plus, 2 NO3- from that first product. And then we have silver sulfate with an S next to it, solid, so that one we're not going to break up. All right, so very similar to the last problem, just different combinations of reactants and products, but once again, we're going to separate all the reactants into ions because they are soluble ionic compounds. On the product side, only the sodium nitrate, which is soluble, and then the silver sulfate remains as a solid. And then to get net ionic equation, we just need to take out the spectator ions, the ones that are ions on both sides of the arrow. And so we see that we have 2 Na plus, one on each side, one on the left, one on the right. And then we also have 2 NO3- on the left and the right. So sodium and nitrate are the spectator ions. We want to get rid of those to write our net ionic equation. So the net ionic is going to have 2 Ag plus, SO4 2-, both aqueous. And then on the product side, we're going to have the solid that they combine to form, which is Ag2SO4. Okay? So this is pretty typical for how ionic equations work when we're dealing with precipitation reactions. All right, any questions on those? So what we're going to close with today is another type of aqueous reaction that actually has some similarities to what we just covered, which is acid-base reactions. In some sense, in this type of reaction, we're still also swapping cations and anions. The difference is that one of our cations is no longer a metal-based cation, it's H+, which comes from the acid. But let's review what acids and bases are and define them a little bit more clearly. So an acid is, we know sort of the general formula of an acid because we talked about them back in chapter 3 and a little bit at the beginning of this chapter when we talked about electrolytes. But an acid is a compound that releases H+ when it's dissolved in water. All right. Now there are other definitions of acid that we won't cover in this class, but you'll see next semester if you take Chem 2. But this is the definition that's fine for us. It's a compound that releases H+ when it's dissolved in water. And we should already be able to recognize the chemical formula of an acid because we introduced that a while ago. So a typical acid has hydrogen at the beginning of the formula, some number of hydrogen at the beginning, and then X, where X is an anion. Either a regular monoatomic anion or a polyatomic anion. And then N is the anion's charge. Basically, however many hydrogens in the formula are going to be how many you need to balance the charge of the anion. Okay, so this is the general formula of an acid. When we dissolve an acid in water, we're going to separate this into H+, the hydrogen, plus whatever the anion is. So that's where this is leading to.
Professor?
Yes?
Didn't they have acid and base covered on chapter 3 prior to the first exam?
We talked about the nomenclatures of acids. We didn't really talk about their chemistry, though, which is what we're covering now. So I'm just reviewing some of the definitions in case people forgot. And then we'll go through some of the new chemistry involving acids and bases, okay? All right, so then a base is, we haven't really seen bases yet defined in any sort of rigorous sense. So a base is a compound that releases OH- when you dissolve it in water. And the vast majority of bases that we'll see in this course, particularly since we're dealing with aqueous reactions, are going to just be metal hydroxide salts. So hydroxide is an anion, and if you have an ionic compound that contains hydroxide and it's soluble, when you dissolve that in water, OH minus is going to be released as an anion. So most bases are going to be some metal cation with hydroxide as the anion. And again, the number of hydroxides that you have is going to be the charge of the metal to balance that and make the neutral ionic formula. So whatever the charge on the metal is N, that's going to be how many hydroxides you have. So most bases are just soluble hydroxide compounds, the very common ones being the group 1 hydroxides like sodium hydroxide, potassium hydroxide. Other soluble hydroxides like calcium, barium, and strontium would be ones that we might see at times as well. So these are typically what we're going to see as a base. It's just an ionic compound that has hydroxide in it, so not too difficult to identify. And then we also have, within acids and bases, we have strong acids and strong bases, and we have weak acids and weak bases. We did discuss this a little bit at the beginning of this chapter, but let's discuss it in a little more detail. So now that we sort of understand the concept of when you dissolve a compound in water, if it's ionic, it could potentially separate into ions. That's really what happens with a strong acid and a strong base. So a strong acid or base is one that when we dissolve it in water, it completely separates into or dissociates, as we often say, into its ions. And as we said at the beginning of this chapter, these are going to form strong electrolyte solutions, ones that conduct electricity very well. All right. So what we want to be able to do is identify which ones are strong acids, which ones are strong bases. So the strong acids that we're going to have, I think we had listed these before, but just to remind ourselves, most of the halide acids, or the group 7 ones, HCl, HBr, HI, those are all strong acids. So those are fairly easy to identify because they all come from the same column of the periodic table. And then there's 3 with polyatomic ions, HNO3, HClO4, caloric acid, and then sulfuric acid, H2SO4. These are the strong acids, which means when we dissolve them in water, they completely separate into H plus in the anion. So if we dissolve HCl in water, much like an ionic compound breaks up into ions, HCl breaks up into H plus as one ion and Cl minus as the other, and that's what defines it as a strong acid. And then strong bases are just going to be any sort of soluble hydroxide compound. So most bases are strong bases that we'll see in this course. So all the group 1 hydroxides, lithium, sodium, potassium, rubidium is next, and then cesium. All the group 1 hydroxides are soluble hydroxides, and thus are classified as strong bases because when we dissolve them in water, they completely separate into the cation and the hydroxide OH minus. And then the other soluble bases that are very common are the heavier ones from group 2, as we said, being an exception to the solubility rules for hydroxide, calcium, strontium, and barium. So all 3 of these, when you, in addition to the ones above them, when you dissolve them in water, they separate completely into their ions, they release OH minus, and that then classifies them as a strong base. So for weak acids and bases, we're not going to really discuss these in great detail in this course. At least you'll get a lot more about this in the next semester of chemistry. But weak acids and bases do not separate completely when we dissolve them. So they do not completely dissociate. And so what that means is that most of the molecules that you dissolve, they don't break up into ions, they stay intact as just that molecule, okay? And so the common weak acids, there's a lot more, but the ones that we'll see a lot are going to be, so HF, which is the other of the group 7 acids, that one is weak. The rest, HCl, HBr, HI, are strong. Phosphoric acid, H3PO4, and then acetic acid, which can be written in a couple different ways, but I'll write it as CH3COOH. This is the acid of acetate with the acetate anion. Those three are common weak acids, and what that means is that when you dissolve these in water, so if we dissolve HF in water, most of the molecules stay as HF, with the hydrogen and fluorine still bonded to each other. You'll get a little bit of H plus and a little bit of F minus in solution, so there's going to be some acidity to that, but it's not a strong acid. All right, and then the only weak base we need to know, which I think I introduced a little bit earlier, but just to remind ourselves, there's more than this, but the only one that we'll see in this course is ammonia NH3. Now, it might not be obvious. How is this a weak base? It doesn't have OH minus in it. It doesn't have hydroxide in the formula. So what happens is that when you add this to water, you don't get full conversion. It's only a small part of this that's going to react, but you're going to get NH4 plus and OH minus. And so basically one of the hydrogen from water gets transferred to the ammonia, and you make these two, and so the formation of OH minus is why this would be classified as a base. But again, this doesn't happen to a great extent. When you dissolve ammonia in water, most of it stays as NH3. A little bit of it's going to react with water to make NH4 plus and OH minus. So that's strong acids and weak, strong versus weak, and that's important to keep in mind, because now what we're going to talk about is how acids and base react with each other. And there's going to be some slight differences depending on whether it's a strong acid and a strong base, or if a weak acid or a weak base is involved, particularly in terms of how you write the ionic equations. The overall reaction is not too different, but the ionic equations can differ. So the first thing to keep in mind with acids and bases is that if we have a strong acid reacting with a strong base, they're always going to have the same net ionic equation, okay? And we'll see how this can work in a couple examples, but the typical net ionic equation for an acid-base reaction, again, particularly if it's strong acid and strong base reacting with each other, is going to be H plus from the acid. Remember, that's going to be what's released by the acid when it dissolves. OH minus from the base. And let's make a prediction here. If we put H plus and OH minus together, what do we make? Water, H2O, okay? So this is the typical net ionic equation for a strong acid, strong base reaction. The H plus from the acid reacts with the OH minus from the base, and you get H2O. And then the spectator ions and the coefficients that are involved in the overall equation depend on the identity of the acid and the base. All right, so they don't always react. The acid and the base itself do not always react in a 1-to-1 ratio, even though the H plus and OH minus do in the net ionic equation. So there's going to be some variations in coefficients, some variations in what the spectator ions are. That depends on which acid and which base you're reacting with each other. But the basic form of an acid-base reaction is going to be your reactants are the acid and the base. And then the products are we form water from the combination of H plus and OH minus. And then the ions that are left behind, the anion from the acid and the cation from the base, they combine to form an ionic compound. So your other product is going to be an ionic compound of some sort. And so this is the basic form of any acid-base reaction, pun not intended. So acid plus base makes water plus ionic compound, where the ionic compound, as we said, the cation comes from the base, whatever was paired with OH minus in the base reactant, and then the anion comes from the acid, whatever was paired with H plus in the acid. I don't have any any examples in today's notes where this happens, but keep in mind, because you're forming an ionic compound, you should still think about solubility rules. It is possible for an acid-base reaction to also involve precipitation. If the ionic compound that you form in an acid-base reaction is insoluble, it will still precipitate like it would in any other precipitation reaction. So there's the possibility that the ionic compound forms as a precipitate. It's not very common. Most acid-base reactions, the ionic compound stays in solution, and the two ions that make it up are considered spectator ions. But in rare cases, depending on the combination of acid and base you use, you could form an ionic compound which is insoluble and thus would also involve precipitation in addition to the acid-base chemistry. So both of those can happen together. The most common situation, all the ones that we'll see today, that's not the case. So let's go through some examples of writing equations for acid-base. So let's do in many cases, and again, for acid-base reactions, coefficients are usually pretty small, and so 1 to 1 is pretty common. So if we have nitric acid, HNO3, and then KOH, potassium hydroxide, those are the two reactants in this one. Remember, the two products are going to be water and an ionic compound. The ionic compound is going to include this cation, which is K+, this anion, which is NO3-, so it's going to be KNO3. Okay? So we just take the leftover cations and anions from the acid and base and make an ionic compound out of them. All right, so this H2O we typically write is with an L because it's a liquid, and then KNO3 is soluble, so we'll write it as AQ. Now to do coefficients for acid and base reactions, I mean, you could just inspect the whole thing and try to make sure it's balanced. The way that I like to think about it is look at the number of H plus and OH minus that your acid and base have. So how many H pluses does our acid have? 1. How many OH minuses does our base have? 1. Remember that those react with each other in a 1-to-1 ratio, the net ionic always being H plus plus OH minus going to water. And so since our acid and our base each have 1, then we just need 1 of each to make sure that the H plus and OH minus react with each other correctly. And if it's 1 H plus and 1 OH minus, then it makes 1 water molecule, so this has a coefficient of 1. And then finally, the ionic compound also has a coefficient of 1 because there's only 1 of each of those ions. So in this case, no coefficients are needed. It's a 1-to-1 reaction on the reactant side, and you just form 1 equivalent of each product as well. But if we go to sulfuric acid and potassium hydroxide, sulfuric acid has a formula of H2SO4, and we're using the same base, which is KOH. Then we're going to form water, and then we're going to form an ionic compound. So the ionic compound is going to be potassium combined with sulfate. Potassium is +1, sulfate is -2, so that's going to be K2SO4, potassium sulfate. That will be soluble because it has potassium in it. But in this case, we're going to need some coefficients to balance it. A few different ways of looking at this, but the way that I like is, okay, look at our acid and base again. This time the acid has 2 H pluses. Our base still only has 1 OH minus. We need equal numbers of H plus and OH minus for our Ionic equation. So if we have 2 H pluses, we also need 2 OH minuses, and so we have to put a coefficient of 2 in front of KOH. And because we have 2 of each, 2 H plus, 2 OH minuses, we're going to form 2 H2Os as a product. And then that one does not need a coefficient because there's already 2 potassiums, 1 sulfate, 1 sulfate. So again, coefficients for acid-base reactions are, I think the largest you'll ever have is like a 6 in front of water, and that's in a really weird case. So again, relatively small, but I think a helpful way to think about it is just make sure that you have the same number of H plus and OH minus. That will get the reactants balanced, and then from there you can do the products. And especially since when we start talking about acid-base stoichiometry at the end of this chapter, the most important thing is to have the correct coefficients on the reactant side. In most cases, we don't care about the coefficients on the product side when we're doing acid-base stoichiometry. So as long as you have these coefficients correct, that'll usually take care, the rest will take care of itself in that problem. All right, and then the last one we're going to talk about is one that involves a weak acid. So the net ionic equation for strong acid and strong base is just H plus OH minus makes water. But let's see what the net ionic equation looks like if we have acetic acid and barium hydroxide, where acetic acid is a weak acid. Okay? So we have to keep in mind what type of acid it is when we write the net ionic equation. So if we start with the molecular equation, we would have acetic acid is CH3COOH, where this is the acidic proton, the H+. These three are not acidic. So acetic acid just has 1 H+ in the formula, if that wasn't obvious. The other reactant is barium hydroxide. Barium is Ba, I should have told you that, but barium is over here in group 2. So it's a 2+ cation, meaning that the formula for barium hydroxide is going to be BaOH2. So in the molecular equation, which we're starting with, these are both going to be aqueous. They're both soluble in solvent solution. And then in the product side, what we're going to get is any acid-base reaction, whether it's strong or weak or any combination, is going to give you water as a product because we still have the H plus from the acid, we still have the OH minus from the base, so we're going to get water as one of our products. And then the other product is going to be an ionic compound that includes the cation and the anion. So it's going to be barium as the cation combined with acetate as the anion. Barium is 2+, acetate is -1, so we need 2 acetates to balance that, which we can write in a couple different ways, but I'll write it like this. Acetate compounds are always soluble, and so that's going to be AQ, okay? Acetate is one of those special anions that's always soluble from the first solubility rule that I gave you. So these are reactions from products. Let's make sure they're balanced. So again, doing the same analysis as the last one, our acid has 1 H+, our base has 2 OH minuses. We need equal numbers of those, so we have to put a coefficient of 2 in front of the acid. So now we'll have 2H+, 2 OH minuses. That gives us 2 waters, and then this is now already balanced. We don't need a coefficient for that. So that's the total molecular equation. And then again, to get to net ionic, what's sometimes helpful to do is to write the total ionic equation. And so this is the molecular equation that we started with. Now we're going to write the total ionic equation, which again involves separating the appropriate species into cations and anions. For precipitation reactions involving only ionic compounds, we just separated everything that was aqueous. Everything that was dissolved separates into cations and anions, because that's what happens when you dissolve an ionic compound in water. But for acid-base reactions, for the ionic equations, we need to think about what type of acid and base do we have. Is it a strong acid or a weak acid, strong base or a weak base? Our base in this case is strong. Any of these hydroxide salts is going to be a strong base, but acetic acid, as you'll recall, is a weak acid. And so that means when we write the net ionic and total ionic equations, we don't want to separate acetic acid into ions. Weak acids do not completely dissociate. They're mostly going to be intact. So for an ionic equation, we don't want to separate this. We just want to leave it as is. So because acetic acid is a weak acid, that's going to determine that we don't separate it into H+ and anions on the left side of the equation. So what that means is that for the total ionic equation, on the left side, we just have 2CH3COOH, still AQ, but not separated into cations and anions because it's a weak acid, not a strong acid. Barium hydroxide is a soluble ionic compound, so that one we will split up. We get barium 2+, and then 2 OH minuses. So because it's a soluble ionic compound, it is going to separate into ions, as we talked about before. And then on the product side, we have water. Water is a liquid, so that's not going to get divided up in any way. That's just going to be 2H2O. And then our other product, which is the ionic compound, is soluble. So because it's a soluble ionic compound, this one we will split up into ions. Barium 2+, and then 2 acetates, 2CH3COO- acetate, also AQ. So we only separate soluble ionic compounds or strong acids in these equations. This is a weak acid, so it does not get separated into its individual ions. And so then finally, to get to the net ionic equation, we have to figure out any spectator ions. And in this equation, there's only one spectator ion. It's only barium 2+ that appears on both sides of the equation as a dissolved ion. We don't have OH-, we don't have that on the right side. Acetate, we don't have on the left. So there's only one spectator ion, which is barium 2+, which means that's all we have to get rid of for the net ionic equation. So our net ionic equation is going to be 2 acetic acids, two OH minuses, and then on the product side we have 2 waters and 2 acetates. All right, so net ionic equations do become a little bit more involved when we're dealing with weak acids, but the same principles apply. We separate things into ions that are appropriate to separate, being ionic compounds or strong acids, and then everything else we leave and we just cancel out spectator ions. All right, so that takes us to the end of acids and bases. I hope all of you enjoy your spring break, and we'll come back afterwards to finish Chapter 6 and get ready for the second exam.